So we left off in the previous video talking about the number of possible BST representations for a given set of elements, and we said that if this was our set of elements and we had ordered them, they have to be unique, of course, we can't have duplicate elements in a BST, and we had ordered them in ascending order, ascending order, and we wanted to place them in a BST tree, then the way to find the different representations would be to look at every single node and to let it be the root of our tree, and then have the ones to the left go all in the left hand side, or the left child, and the ones to the right be placed in the right child, or the right subtree. And keep on doing this recursively until you find all the number of possibilities that you can get. So let's assume that we were looking at element I here, and we were to place this as our root. Then we will have I minus 1 elements smaller than that particular element we're looking at, since they are all ordered and sorted, and then we will have n minus I elements that will be larger. So these will all be placed in the right subtree, and the I minus 1 nodes will be placed in the left subtree. So if we were looking at this particular node, then the number of possible BSTs that we're going to get with node I at the root will be applying the same recurrence relationship to I minus 1, because we're basically doing the exact same thing but looking only at this subtree, which is a tree of itself, and multiplying it by the number of possibilities for this particular subtree. And you would have to multiply, of course, because every configuration is independent of the other. So every configuration could have all the others as one, any of the others as one of their as the other branch. So this would be the number of possible BSTs that we can get with node I at the root. So do the same thing, but now not only for node I, but for I going from 1 to n. So for all of our elements, then you get the summation, and this would be your recurrence relationship. So this would give you the possible number of BST configurations for a given set of elements, placed in their proper order from 1 to n. So for example, if we were to look at, and these are the base cases. So if we're looking at the case where we have a set of 0 elements, then this is the empty tree, and there's only one possibility for it. If we're looking at the set of 1 element, then the tree will always be just that element, so there's only one possibility for it. So if we were looking at this set, ABC, as our example, and if you did the calculations putting n as equal to 3, you would get 5 different possibilities, and here they are. We have A, B, C, so B is less than C, so it's placed in its left node, left child node, and we have ABC, and then we put B as our root, and we have A, B, C, and then we finally put C as our root, and then we have A, B, C, and then again the same thing here. So these are all our 5 representations. So this was just a note on the side. Now we get to the operations that could be performed on a BST. A BST is an abstract data type, so we have to define the operations. We're going to be looking at a few of them. There could be multiple more. We're going to be looking at finding the minimum, finding the maximum element. These are pretty simple. Finding a particular element or key, adding a key, and this will be the most complicated. Actually, we won't be looking at removing a key. We're just going to be removing the minimum. So first, let's look at finding a key. Finding a key you would have to pass it the tree, the root of the tree, and the key that you're looking for. If the root, this is the base case, this is where you actually found your key. If the key is less than the root, what you're looking at, then you're just going to call that recursive function once more, but limiting yourself to the left subtree, because you know that it's less than it, so everything to the right could be ignored. If the key is larger than the root, then you're going to perform the same call, but this time with the right subtree, because everything to the left could be discarded, since you know your key is larger than that. So if you reach a point where we get a root is equal to none, then the key was not found. Or if you get the root is equal to the key, then that was found, so you just return that root, whether it was found or not. Finding the minimum is very simple. You just keep on calling finding minimum on the left until you get to the very last, which is null. So if root.left is null, then we know there's nothing left, so we've reached the very end, so we return that root. And if it's not, then we're just going to keep on going to the left until we reach the very minimum.